I'm Andy, and I'll be discussing our work on automated high-level synthesis, design modularization via EGRAPHS' Anti-Unification. This work was done while I was at Georgia Tech. And yeah, let me just get straight into it. So I'll start by giving some background and motivation on what hardware design with high-level synthesis even looks like, the importance of design modularization, and then dive into some background on what EGRAPHS' Anti-Unification even is and why it's particularly useful in this case. So for those of you who aren't too familiar with high-level synthesis and hardware design, high-level synthesis, commonly referred to as HLS, basically can convert input programs written in a high-level language, such as C++, into actual hardware. And this hardware directly accelerates the exact function or like purpose of your program. So this is what this kind of flow looks like. You have a function or a set of functions written in a high-level program, and then you get an accelerator computing that. So then you can obviously do this for many different programs, each one synthesized into its own accelerator. So the main thing I want to highlight here is that how you write your input program directly influences the quality of your hardware. So the code structure in C++, namely your loops and functions, directly determines the properties of your hardware. So some things you can see here is like when you have a loop, you just instantiate your functions once, and you're going to repeatedly call them. Whereas if you have like an unrolled loop where you have multiple instantiations of a function, you get many functions acting in parallel. So obviously, in this case, we have 3 input programs, and we're generating 3 unique hardware designs, 3 unique accelerators. However, you might have noticed I used the same functions, f, g, and h, across all 3 input programs. And we've basically instantiated them many different times across the different hardwares, even though we're using the exact same hardware modules. So this is a property of our modern HLS tools. That's how they were designed. And this basically makes them really good at automatically synthesizing accelerator hardware. You can write an input program in C++ and then automatically generate the accelerator for said input program. However, this is not really good for synthesizing architecture hardware. So what I mean by architecture hardware is if you think of your traditional CPUs, GPUs, when you have an input set of programs, they all run on the same set of hardware. You don't get 3 separate instantiations. But as you can see, HLS isn't really optimized for that. And that's due to you would have to write your input program itself describing an architecture as opposed to just a function. And then this kind of interacts with how our modern workloads look. So AI and ML workloads have like really benefited from custom hardware recently. And they're constantly evolving, your ML models. However, they constantly reuse the same key operations. So this includes like your gems, your convolutions, your attentions, and your activation functions. So our hardware is the same across iterations, but if we were to use HLS, we're constantly generating new sets of hardware, even though we're basically doing the same thing. And then AI and ML workloads and other modern workloads have shown to benefit from highly specialized architectures as opposed to really, really specialized accelerators. And then finally, so what design modularization really is it forms the basis of what's in an architecture, because if you modularize your design, you determine what are the common compute units, and these are going to be the basis of your architecture. However, in both high-level synthesis and traditional hardware design, it's highly manual, tedious, and then therefore error-prone. So you need to determine what is going to be a common module, how you're going to use it in each of your programs, etc. So really, this becomes an issue because HLS's original promise was it's going to be easy hardware design. It's going to be much easier than RTL. You just write your programs, and we're going to give you good hardware. However, right now, it's just as difficult as RTL to go and modularize your design. And you have to do a lot of manual work. So we're really failing on that promise. And what I want to highlight is for HLS to continue to deliver on said promise, we need to support this automatic design modulation. We need to be able to determine a set of common modules for an input set of programs that's going to form a common architecture, something like this diagram on the bottom right. The next generation of HLS flow should take in many input programs and then determine the best common architecture for these input programs. And that's exactly what we want to show in this work. So on the left, you have our current HLS flow. On the right is the next generation that we envision. And to bridge the gap, really what you need is a way of doing automatic design modularization. You want to find out what are the common functions shared across our input programs, put these into an architecture, and then run these P1, 2, and 3 as instructions over this architecture. And that's exactly what I'm going to focus on in this work, is how we perform this automatic design modularization. And spoiler alert, it uses EGRAPHS'. So a few years ago, some of the members in this audience, they developed a tool called Babel. And what Babel does is explores library learning via a programming languages technique called Anti-Unification. And by library learning, that means when you have an input set of programs, you're exactly doing learning common functions that can be used across the input set of programs. What anti-unification is if you have some expressions, it's a way of determining a function abstraction over these expressions. And equality saturation can really help in this case because you can expose many equivalent representations of your expressions to find better or more general functions. And in Babel's case, so they provided this framework that can do the EGRAPH anti-unification, and it was highly motivated by program compression. So finding a common library which minimizes the overall program length. And then we want to basically take these same ideas of library learning and apply them in hardware, because when you find hardware common functions in your HLS designs, this is going to equate to a common hardware module in an architecture. So step one is to actually explore equivalent representations of our input HLS designs so that we can learn useful hardware modules. So that's step two, is learning these actual function abstractions. And then step three is when we have a function and then a modularized implementation, we need to select the best one for our hardware. So as I mentioned, the first step is really exploring the HLS design space. And HLS is particularly, loops are a very common structure in HLS. So I'm going to basically be going over how we analyze loops and explore loop transformations. So let's say we have our input design over an IR in the EGRAPH, and we have a bunch of loops. So common loop transformations are loop unroll, loop reorder, loop tiling, all the ones you're familiar with. But you also might know that you can't apply these to every single loop. There is some validity check. So we do need our loop transforms to preserve equivalence. And primarily for loop unroll and loop reordering, this is due to the memory accesses. And luckily, there is a technique for finding out when loop transformations are valid, and that's using something called polyhedral loop analysis. So we're going to use that to try and determine the validity of unroll and reorder before we go and apply them. One other issue, as many people have talked about today, is the scalability of our eGraphs. When you go and try apply every possible loop transform to every possible loop, you're going to blow up your eGraph, you're going to run into a scalability wall, and you're going to kind of prevent anything useful happening. However, in this case, when we explore the design space, it's not to optimize our program. It's more to find out which loops are similar and can match, so we can find a useful function abstraction. So it'd be really useful if we could know that beforehand and only apply the transformations there and not blindly. And luckily, so that's exactly what we want to do. And luckily, polyhedral loop analysis also provides a technique for doing this, or at least the structure does. So we're going to use that to find similar loops and then conditionally apply these rewrites on those loops so we don't continuously blow up our eGraph. And I'll kind of get into how we do both of these things. But before that, the key part of polyhedral loop analysis is the polyhedral representation of our loops. I don't know how familiar the audience is with this, but basically you have a domain for a nested loop, and this is the space for each of your iterators. It's just effectively your loop bounds. And then you also have a map which says how the iterator space maps to memory accesses, both reads and writes. So let's get into the first step, which is how we're going to use polyhedral loop analysis to determine the validity of our unroll and reorder rewrites. There's many libraries that can do polyhedral loop analysis for you. We use the integer sets library because it's kind of agnostic of your input language that your loops are represented in. And they have an object and a method called the ISL schedule. And the ISL schedule contains exactly the information we need, which is permutability, which tells you whether a loop reordering is valid. And it contains a term called coincidence. And what coincidence is tells you whether a particular loop can be unrolled or can't. So in this given example, we have a simple for loop here computing a matrix multiply. Your domain and schedule are fairly trivial in this case. It's just the loop bounds. But then the ISL schedule object correctly identifies that this nested loop is permutable, as you can see. And then also the coincidence in this case is 110, which means that loop MMI and MMJ can be unrolled. There's no dependency between each iteration. But loop K can't, and that's due to the accumulation over that dimension. So we're going to use this information for our rewrites. Before I get into that, I'll also talk about how we're going to use the polyhedral loop analysis to address the scalability issue of only finding loops that we know are similar. So to do this, we introduce a structure ourselves called a loop group. And what this loop group is, it contains loops that have the same memory accesses after some permutation of the iteration order. And we're basically going to use this to find out which loops we believe are going to be similar because their memory accesses are similar. So what this looks like, it will help with an example probably. So on the right, we have two programs, each having their own implementation of a matrix multiply. There are two programs that are almost identical, except that the loop we do the accumulation over, k and p1 and z and p2, are in two different spots. They're swapped, mmz and mmy are swapped in p2. So we know these two programs are equivalent, and we basically want to try and match these two loops. So the first thing we need to do is compare the memory accesses in our loop. And thankfully, the polyhedral representation has this easily available to us. And then we're basically going to use that to then permute different orders and see if these memory accesses match. And that's exactly the next step. So as you might have intuitively noticed, and as I mentioned earlier, these two loops are identical and do have the same memory accesses once we permute mmz and mmy. And that's exactly what the mapping in the loop group is trying to show. MMI in this case was the first loop, so it's kind of identity. But then MMX highlights that you need to swap loops 2 and 1. And then this mapping is exactly the reorder we need to match these two loops. And it also highlights which loop depths match. And therefore, we're going to search for tilings over these matched loop depths. As this would suggest, there could be a common function here that we might want to take advantage of. So summarizing all of this into how this builds into the eGraph and the rewrite flow, this is the top path when we take advantage of the integer sets library. We create an ISL schedule, and then we extract the unroll validity. And then we're effectively going to create a dynamic rewrite for loop unroll, which is only applied when this unroll is valid. Similarly, you're going to take the polyhedral representation, create a loop group, and use this to determine the order mapping we're going to need for loop reordering. And again, we then add in the reorder validity from the schedule with the reorder permutation, and that tells us when we want to actually apply loop reordering to loops in our input program. And finally, you then take the order mapping, and then here we're determining a tile size using the greatest common denominator of our domains. And this is basically guaranteeing we're going to find a common loop that can tile both. And then this tile size goes into the loop tiling rewrite. So these three rewrites are then going to be just applied over our input space, and we're going to explore not an insane number of loops, only the ones that we know will match. So once we have this space, we now need to get into how we actually perform the hardware module learning. And this is the main section, which is going to use Babel. So as I mentioned earlier, Babel does do library learning over our eGraphs with anti-unification. So the question obviously arises, can we just use it? Can we just plug in our HLS designs? And can we extract really good hardware? As you may have suspected, the answer is no. And that's mainly because minimizing the program length doesn't correlate with really good hardware. And the main reason for this is good hardware needs two things. One, it needs to be synthesizable. And what I mean by that is not every C++ program can actually be converted into hardware. So we need to make sure we can do that. And then we also need really good hardware performance. And this is power, performance, and area, typically referred to as PPA metrics. So we also want to make sure our final design optimizes this as opposed to some notion of program compression. And obviously, this then leads us to the next step. We want to adopt Babel and adapt it to use hardware-oriented cost functions. So before I get into what our cost functions are, let's try and summarize exactly what we want from our designed hardware. So number one is you want your modules to be synthesizable. You want modules to be meaningful. This is inspired by, in traditional computer architecture, each compute unit has a purpose. It means something. It's not just arbitrary arithmetic functions. And you want it to be holistic. I'll kind of get into why this is important, but you basically don't want to be splitting up functions that do this, that are highly related. Number two is that we need to ensure that the final hardware design actually optimizes our PPA metrics and not abstract notions of meaningfulness or holisticness. So again, a simple example here should help. In this example, where you have two programs, each computing a dot product, one of length 8 and one of length 24. And I've given three different ways of how you might do this in a hardware module. So example one has no modularity. Program one does its dot product, and program two does its. Program two uses a common module, which is the multiply accumulate. And then both dot products can use that. And then program three actually has a dot product as its common module of length 8, where program two then tiles this 3 times to compute its dot product. Obviously, we can compute a bunch of different costs here for arbitrary cost functions. And in this case, the three that we're going to be comparing is the babble cost. So this is the naive program length cost over our eGraph. And then the other two are introduced in this work, and this example is going to hopefully motivate their existence. So the first is the hardware impact cost, and the second is the hardware performance cost, each trying to target like requirements 1 and requirements 2 respectively. And we'll kind of get into where they come from and why they're important. So let's analyze. And then, yeah, before we do that, the thing you need to recognize in this example is the no modularity case. They each optimize a different cost. The no modularity case is actually minimizing our program length. The middle case minimizes our area. And the final example is minimizing the hardware impact cost. So when we think about the no modularity, obviously there's no shared hardware module. And this is actually failing both requirements. So no module, you fail requirement 1. But then because you didn't find a hardware module, you're actually reusing the same functions multiple times. You're wasting area. And therefore, you're failing requirement 2. So clearly, this isn't a good cost metric to optimize for hardware. In modular 1, I would still argue you fail requirement 1. This is because you're not capturing the full dot product. So while it's synthesizable and meaningful, it's not particularly holistic because you're separating the operation. And the reason this is really important is while the produced hardware is hardware friendly, it does minimize area. By separating the operation from the loop, you can't perform loop optimizations here. And then you can't minimize your delay even further. So I would also argue that this isn't particularly optimal. Which leads us into modular 2. So here, the shared hardware module is our dot product. So it is synthesizable, it's meaningful, and it is holistic here, capturing the whole operation. And then therefore, when you capture this whole operation, if you want to go unroll this loop or perform further optimizations on this loop, it exists in the function, and you can further optimize your PPA. Hence why, in this case, both your hardware impact costs and performance costs are minimized. So so what does this teach us? Is that we actually want to decouple the stages and our cost functions. We want to find out which hardware modules to use by using the hardware impact cost, as this kind of targets when hardware requirement 1 and which modules are very useful. So that's what this looks like. It's like which modules should exist in the shared hardware. And then we're going to use the hardware performance cost when we have an explored eGraph with function modules to then extract the design. And this is basically equivalent to telling us how we want to implement these shared hardware modules and what's the best way to minimize PPA. So let's get into what these hardware cost functions actually are. So we have the hardware impact cost. What this does, the key takeaways here are that we assign a cost of 1 to every arithmetic and memory operation, no matter how expensive it actually is in hardware, more to just kind of a notion of like it's one hardware operation. It's like some abstract notion of like importance. Our for loops are proportional to the number of iterations they take, and then the cost of the body. Two things we do here is that variable bound for loops are given an infinite cost. That's because this isn't particularly synthesizable or hardware friendly. And similarly, if the loop body doesn't use the iterator, we deem this not to be a very useful hardware function. So those are also given infinite costs. The costs of our functions is just the cost of the arguments, ignoring the cost of our primitives, because when you implement them in hardware, those don't really serve any purpose. And then when we recurse over the eGraph, this is almost exactly as it's done in Babel, where we count the cost of the function only once, as a hardware implementation will only instantiate a function once. So the hardware performance cost is a weighted sum of the area and the delay. I won't go too much into this, as this is basically just proportional to the gate costs. But the main thing here is that, I guess, delay, when you recurse over the eGraph, uses a maximum recursion, whereas area is more similar to just a sum. And again, you only account for functions once. And this summarizes, I guess, both cost functions, and I guess there's more in like the paper. But the two most important things here is that the captured metric by our hardware impact cost is synthesizability and trying to be important, which is proportional to the number of hardware operations taking place. Whereas the hard performance cost is a better model of PPA, trying to capture both hardware area and hardware delay. So let's get into some of the results. So and like, does this actually work? And the answer is yes, to some extent. So this is just some examples of automatic modularization. In blue is input HLS designs, and then in green it's the output of our tool, which are all modularized, where the module highlighted in red is shared across the output designs. So we're able to do this over arithmetic equivalences, loop unroll equivalences. The case on the left is kind of interesting, which where program 2 has a dot product, and program 1 is a complete matrix multiply. And as we know from math, you can actually compute your matrix multiply using just dot products. And that's exactly what our tool can automatically identify in the output. Continuing along this line of reasoning, we have a loop reorder case as well, where you're learning common functions over this reorder, and then a tiling. And then probably the biggest case we handle right now is a matrix multiply tile. And what this is you have two programs, each computing a matrix multiply themselves of different dimensions. And then you're going to find a common tile that can be used to compute both matrix multiplies, significantly reducing your area. So that's what this table shows, is just the area change after modularization. I'm not really showing this to point out any significant area saving, because this is quite obvious. If you share hardware and you use less, you're going to use less area. But it's more to highlight that we can actually automatically identify the shared hardware module reuse. I also don't really mention delay or power, and that's because until we have a proper way of executing these designs with sharing and a proper way of scheduling and executing, the performance and power estimates from HLS don't really make any sense. So thankfully, one of my lab mates is working on that problem itself. One thing I want to really highlight is in previous iterations of this work, and actually in this diagram, there's only 2 for loops for our matrix multiply tiles, so it's actually not complete. And that's because before we introduced polyhedral loop analysis, we actually couldn't, because our EGRAPH was way too big. We couldn't identify the proper common function. And we used to take 180 seconds to not even do that. By introducing polyhedral loops analysis, we've really solved the scalability problem, finding the complete tile in only 20 seconds. And then the last point here is that we can do this on GEM, general matrix multiply, which is already a very useful and common operation in your ML, in the ML world. But also other ML operations are just nested loop operations, such as convolutions, attentions. So this similar idea of tiling and reuse can be exposed there. And then finally, just before I go, I want to highlight some future opportunities that these architecture-oriented HLS tools are going to open, we believe. So this is mainly to do with architectural DSE. So imagine you wanted to create a hardware architecture. You had a couple of programs you want to run. So let's say it's 2. You have A and B. So you can just create the most optimal architecture for these 2 input programs, highly specialized and flexible enough to run either one. But then you come along, and next week you have program C. You're like, OK, I also want to execute this. So now you want to create the best hardware architecture for A, B, and C. And you keep doing this, so D, and you can keep adding as much as you want. Obviously, the more programs you run, you have increasing flexibility of your architecture, but you're also increasing its overhead to be able to run each of these separate programs. And really, you want to ask the question, what is this trade-off? Which of these architectures is ideal for my use case? And having a tool which can automatically generate an architecture based on an input set of programs that's highly specialized to them is going to be critical to exploring this question. One other potential architectural DSE we want to highlight is, in this work, we do tiling. When we tile stuff, we use what I like to call a minimal tiling with the greatest common denominator. So it's the smallest matrix multiply that can tile both operations in this case. But you can also do a maximal tiling, which is the lowest common multiple of your loop domains. And in this case, you're actually creating the largest possible matrix multiply tile that can fit both operations at the cost of not using some of your hardware in either case. So you have really high area, but as a result, you can execute the matrix multiply in 1 cycle as opposed to 8 or 2. And again, which of these common tilings is ideal? Highly dependent on your use cases. And again, being able to automatically generate these architecture is really critical. So this is mainly just to highlight the point that these architecture-oriented HLS tools are super important for the future of architecture and hardware design. Anyways, that's the complete talk. Thank you, and I'll take any questions if we still have time for that.
Thanks for the great talk. This session is, ending ahead of schedule, so we have time. We have a nice buffer before lunch for plenty of questions.
Hey, thanks for the great talk. This is Rachit from MIT and Jane Street. I was curious, so in HLS, oftentimes when you actually want a high-performance design, you're going to use a lot of pragmas.
Yeah.
And unrolling is one of them, but really you want to be pipelining your design, you want to be banking your memories. And so really what you probably want to be able to do is have some notion of a context under which you can extract this loop, right? If you have a loop that is in parallel accessing some memory and the memory is not going to give you the kind of bandwidth you need, the parallelization is useless. So I'm curious if you've thought about having some notion of a context under which this anti-unification abstraction actually makes sense, and how to include things like pipelining, which are not source representable because they're sort of a weird optimization that happens at the hardware level. Thanks.
Yeah, thank you for the great question. Yeah, so this work is basically quite early stages. It's just, we originally wanted to ask the question, can we even do this? Can we find useful hardware modules? Which is what motivated this work. But yeah, you're absolutely right. HLS has all these pragmas, and different optimizations make sense under different scopes. So in my opinion, like a context does make a lot of sense. And this is probably going to go into like your cost function. So under different contexts, unrolls make more sense. Maybe if you have pipelining, you don't want to do that. So I think it is a kind of an open challenge of how you want to incorporate pragmas into the design space and use that to extract. But that's definitely kind of along the lines of this, but even just general HLS optimization in an eGraph setting. But yeah, so right now, we haven't really considered it, but definitely future iterations of this work, it is on our kind of to-do list. Thank you.
Hi, it's Dennis from Google. And basically, a question I have is at some point you have this concept of meaningful design.
Yeah.
And I was really confused. Why do you need that? Because my assumption is you have some costs, maybe they're imperfect, but you really care only about performance. You don't really care if it's meaningful. So why do you need this concept of meaningful design?
Yeah, so basically what kind of motivated that was, I guess it's kind of back here. Oh, yeah. So what we are trying to incorporate with meaningful is we were running into cases where you don't really learn something, you kind of learn something arbitrary, and then it's not actually able to be used very effectively later on. And basically what the meaningful here comes out as is just the number of hardware operations. You don't really care when you learn a hardware operation, like how expensive that operation is to an extent. You want to learn like just the most operations in a module. So that's where that's coming from. And I think it's just more motivated by, so if I have programs A and B, and then you just learn the best, it'll be best for A and B, but we hope that like part of the motivation for this is like when your ML model changes every year, you can still hopefully be able to run it on the same architecture. So being able to extract something a bit more general than just the most optimized, we believe makes sense. But yeah, there does need to be, I think again, a big part of a future direction of this is a big analysis over our cost functions, because we do believe that's like super critical to finding the best architectures. So there is like going to be a huge, kind of like a bigger cost function study of like how do we design the best hardware.
So is it kind of similar to like overfitting? Do you feel like you try to fight overfitting on the inputs you were given?
Yeah, it's exactly that.
Okay,
yeah,
perfect.
It's exactly that. Thanks.
So I thought the incorporation of polyhedral analysis to kind of find common loop, I guess unify loops somewhat, was very cool. And you're kind of doing that outside the eGraph using this ISL library. This is maybe a vague question, but would it be valuable to be able to represent the loops and various tilings or reorderings within the eGraph?
So actually the loops are represented in the eGraph.
Yes, but your reorderings, et cetera, you're doing that externally, right?
So kind of. So we kind of find the reorder externally, but then we have like the loop reorder rewrite is performed on the eGraph. So we have both the original loop and then the reordered one exist in the eGraph. I don't know if that's answering the question or.
Let's just chat afterward.
Okay, yeah, that makes sense. Thanks.
Oh, check. And thank you for the great talk. So it is very interesting to use library learning to learn common architectures. So I have a question about this part. I think one limitation of library learning is that it has a very high requirement on the similarity of the input programs, right? So if you give it a large set of programs, then it may be disturbed by small commonality between a large part of programs instead of a large commonality between a small set of programs. So have you discovered similar problems in your use case? For example, have you tried to put all your programs in all case studies into your approach at the same time and see whether it can learn all the architectures in all case studies?
So no, we haven't quite done that yet, because up until like 2 weeks ago, we were really bottlenecked by the scalability. So as soon as we try to do multiple designs and each one having, let's say, multiple possible functions to learn, the tool will just break. So we're hoping to be able to explore some of that soon. But I can definitely see that being an issue here. And I guess it comes back to your cost function question of how you want to address what is a good library. Do you want it to match all your input programs, or do you want a really big one across 2, but not the rest?
OK, let's thank the speaker one more time.